Hi everyone. So right now we are going to actually learn about RL, especially in the context of RL is reinforcement learning for those of you who don't know, especially in the context of open environments or verifiable rewards. What it means is that we create an environment which gives verifiable rewards to the models so that it can learn the task on its own and learn how to solve the task based on the rewards that it gets. It is how current models are being trained on. Okay, so just a few foundation we have is that um, so what we are going to do, the purpose of this stream is to not teach you anything. It is just to learn with me, alongside with me. I hope you guys do. So this is the very first few lives that I'm doing. So I'm not even sure if it will be useful for you guys. I hope it gets shown to some of you. Let's do it then. Now let's study. First, RL is basically Markov decision processes. The five pillars of Markov decision process is defined as the five tuples: state, action, probability, transition probability, rewards, and discounting factor. State is the state at which the entire model is, the input of your model. Action is the output of your model. Uh, Transition probability is the dynamics of the environment. If an agent takes a particular state and performs a particular action, what is the probability that it ends up in a specific new state? In chess, it is deterministic, but in the world robotics simulation, it is stochastic in nature. That is probability based. So reward is a feedback signal that we give. So in supervised learning, we have cross entropy. For RL, we have rewards. The function of supervised learning is to minimize its loss, but the function of RL is to maximize the reward. Now, discounting factor is given just so that we give more reward to longer context things. That is, we delay the gratification of the model. Yeah. So, so in RL, your network is called the policy. It is denoted by pi theta, where theta is the parameters of the neural network. The policy takes a state as an input and outputs a action probability distribution over possible actions. So it is usually like So it is denoted by phi theta for a particular state and action, probability distribution of action. Your ultimate goal is to find the optimal theta weights to maximize the expected return. There are two main approaches to RL actually. Value-based methods, example Q-learning, and policy gradient method. So I'll also introduce you to another stack, that is resource basically for you to learn. So this is a very good resource, especially this deep reinforcement learning. It's a good resource and it teaches most of the things that you would require in RL. It's not deviate. So yeah, so value-based methods, example Q-learning. So let's learn about that. So instead of directly mapping states to action, the network learns to predict expected future reward of taking a value-based method is basically Q-learning is an example of value-based method. So basically, instead of predicting the action, it predicts the reward of taking a particular action or learns to predict the expected future reward of taking a specific action in. If we select the action, with the highest predicted value, reward of taking a specific action in specific state. This is called the Q value. Q. So value-based methods, basically like Q learning, is methods that basically predicts the reward that you will get from taking a particular action in a particular state. It is denoted by the Q value of a particular state and action. Um, Agent simply selects the action with the highest predicted Q value. This relies heavily on the Bellman equation. Bellman equation is 2 of a expectancy of reward t plus 1 plus discounting factor max plus the max a action stage t plus 1 comma q q. So you can see this is the equation that um, the value-based methods are working with. So it is actually qs comma a and it's potential. Let me write it once without it. Uh, plus 1 plus discounting factor in value of 8 t plus 1 comma action dash or max. This is the value base. Now policy gradient methods like the PPO. These are the policy based methods are the ones that we use from this course. So a lot of things I also don't know. Let's see if okay. So just you might think, why am I talking like this? Well, basically we are learning together, and the reason why I'm speaking out loud is it helps me learn better, and also it keeps me accountable because I know someone is watching. In this case, it is recording. It's a gradient method example, reinforced PPO. Typically optimize a policy network. So in value-based method, you try to find the best value for the action that you take given a particular state. For policy-based method, you directly optimize the policy. Here, you directly optimize that by beta, beta. Higher than average reward, increase the value. So in policy networks, you directly train the policy. So delta theta j theta is equal to expectancy over by theta, then by theta for particular states. AT is the advantage. How much better the action was compared to the baseline. Hmm. It is the advantage. Our goal is to need to see how the guided learning engine works for. So directly onto large language models. This is crucial, which we need to. An agent might play a video game where the action A is press the jump button and reward R is the score on the screen. For LLM, the setup changes. The LLM action space is infinite, right? An LLM can say, "Hey, how are you? How are you? Hey," or whatever. It can just change the sentence, and we need to figure out if it is correct or not. So the action space is infinite, right? It's not like games where games you have a full joystick up and down WASD and few actions like kick or punch or anything. So, but in LLM it can be anything like, so the action space is infinite. How do you do RL then? How? So
Playing from MSR.
So I was looking at the YouTube stats. Yeah. So let's get back to this. Instead of judging the LLM action is generating a sequence of tokens. However, the document emphasizes that your policy is active and rarely valid, just as framework text. Instead, the action is completion that must conform to a specific format like XML tag, JSON, or two for schemas. If the model generates brilliant answer but breaks the format and parts of fails, and the action is effectively invalid. Yeah. The shift in reward judges versus verifiers. Getting a reliable reward signal is the hardest part of an LLM to train. Yeah, because as I said, the action space is infinite and you can do a same task in many different ways or LLMs. Uh, so how do you verify it? Or how do you give reward to it? So few of the things that we have covered as of now is RLHF, that is reinforcement learning with human feedback. RLVR is the one that we are, as a research community, is focused more on. That is reinforcement learning with verifiable rewards. Now, you train a separate model to store how good or helpful the text sounds. The document keeps once again scaling slowly on these findings. These models quickly learn to hack them by sounding. So RLHF, we used to use the very first versions of GPTs, we used RLHF, which basically is good, but it makes the model sounds confident while not being accurate, which is not very helpful, yeah, to be true. So how do you fix it? So we came up with RLVR, so the modern standard for reasoning, coding, and open. Instead of a judge, you use a deterministic success criteria like, let's say, unit tests, exact text matches, sandbox execution, was it able to execute. So basically, we verify things. Now, we can verify by parsing the output and seeing if the series will not be series. We use sandbox usually documents to run code. This leads us to critical distinction in how modern RL environments are built handling state. Imagine the LLMs write the Fibonacci script but makes a small syntax error. The environment executes, catches error, returns the byte traceable to reads the error and generates a step and completion of the code. Like a simple calculator API, each interaction is completely. So multi-turn debugging is something that is important, I guess. The environment needs a way to remember the mistake that it made. So that's it. When you build a stateful tool environment for this Fibonacci task, the environment uses a unique session ID dependencies to keep the Python execution environment active across multiple runs. Based on how LLMs price evolve, why is it crucial for that hidden from the sandbox session? I just kept it because then it will learn because then it can learn to hack it. Well, I hope you guys are also reading a lot because I'm using guided learning and I've given a very good deep research on RL and openenv to learn. So let's see. For infrastructure details, it often stops trying to solve the actual problem and starts trying to solve the environment. So we don't want the LLM to solve the environment, we want the LLM to solve the actual problem. So this is a problem with LLMs that they try to hack it. There is a problem with humans also, right? We try to hack the reward. That's why people, so like in exams, people cheat. They are basically trying to hack the reward of test scores. So similar to, but those who actually cheat won't learn the concepts. So this is what we are trying with LLMs also. LLMs also replicate this. If we give access to the environment, they try to cheat by trying to solving the environment and getting the rewards rather than solving the actual problem. Hidden state in the LLM start showing. We use hidden state injection. That's why we use hidden state injections. An architecture designed to standardize verifiable stateful environments instead of just running a Python script to play to store the state, the tools, and the think about the other beginning process. An agent might generate and execute thousands of random or broken snippets while it explores the why do that open isolate this environment inside government rather than running directly on the host machine because because the LLM can create arbitrary codes which you might not know how it will affect the host machines. So while it's trying to hack the environment or get more rewards, it can execute a code that might be harmful for your host machine. That is why we deploy it using a Docker. Let's start. So, because of this, OpenEnv adopts a unique architecture. Instead of being a simple Python class you can import, an OpenEnv environment runs as a standalone fast API Docker. Here, RL training loop, the client communicates with its container over HTTP. Oh, this client server architecture leads to a profound lesson in the OpenEnv documentation. Two distinct interfaces, agent interface and orchestration. So OpenEnv has two distinct API. Two distinct interfaces, agent interface, the tools and actions the model is allowed to use to solve the problem. Orchestration interface, the controls the training loop uses to manage the simulation. Step based. Hmm. Two interfaces, agent interface and orchestration interface. Sure. Tools agents are allowed to use tools to verify the environment. Controls the training loop used to manage the simulation. Step step और क्या क्या reset step. Separation matters. Imagine you're deploying a trained LLM into a real world production system like Manasi. Training it in a simulation, why must the agent never be aware that function like reset exists? Because then it can have get more. I guess it is nice. Anti-bonanza is saying that it might attempt to call reset during the real world deployment, like when managing a live. So, Simple opponent mandates two distinct interface. Agent interface, the tools that the agent is exposed to, and orchestration interface, the tools that are needed for training the loop, and which we do not expose to the agent. Now that we understand how opponent isolates the execution safely, let's look at how it actually scores the models. In classic RL, an agent might get a +1 for winning a game and 0 for losing. This is sparse code. But if an LLM is writing a complex 50-line Python script, giving it strict pass-fail based on final execution makes learning incredibly slow. It might get 49 lines perfectly right, but fail and get a 0 due to a single missing comma. To solve this, OpenEnv uses a brick system to decompose the reward into verifiable content. If our goal is for the LLMs to write a Python script that fetches data, we use a rubric system to decompose the reward into verifiable. So openenv has a rubric system verify to decompose the reward into verifiable components. The goal is for the LLM to write a Python script that fetches data from AI, passes the response, and computes that. Breaks that down into multi-step rubric that gives the model partial credit to help guide its learning. We can break it down, giving reward for correct syntax of tool call, correct syntax of tool calls, uh, correct uh, response, uh, wait, correct them, correct, correct. Is going to correctly is going to we can penalize the reward if the number of lines is increasing by. But I wonder how do they penalize the number of lines because then it will just try to find hacks to thought. Okay, so it is saying that as a perfect breakdown, you just describe the process you need to check what prevents the mistake of where an LLM somehow guesses the right final answer. Using a composable rubric abstraction which functions very similar to how you stack layers in PyTorch and in a dot module. Each of your 5 points becomes a separate modular scoring function. Ah. However, there is a critical structural element in this called gating. second question. Any of the scores for all five of these independent days are related to process and how to evaluate them in a strict sequence and stop early for foundational stuff. Oh, okay. Thinking about the other rollout factory, the model is generating thousands of items. Environment is constant spinning of problems. Uh, so it's very important. So the question is, why is it important to use gating? So gating becomes very important because you don't want to know after 10 minutes that the initial step itself was wrong. So the foundational steps should be correct. To know, so for the above example of calculating the temperature average, the temperature fetching step should be right. Only then the other steps make sense. Testing expenses few minutes and Docker overhead evaluating logical characters of a script or contains of its syntax. It also prevents the model from receiving a confusing noisy reward. Oh, let's see, again, confusing noisy events along. Now we have a conceptual blueprint for our opening and isolated container, the session ID for stateful tool use, and a gated rubric for verifiable partial threading. Train the LLM using that. This is where the prime RL framework comes in. Instead of running everything in one massive script, prime RL splits the RL loop into three distinct distributed processes. Inference service, often VLLM, rollout workers. These hold the model's weights and rapidly generate trajectories and rewards. Trainer, the mathematical engine it uses PyTorch and FSDP for sharding across GPUs to calculate the loss and update models. Orchestrator, the traffic cop, collects rollouts from inference. Rollouts from inference. Which are they keep interacting with their memory. Hmm. I think you learned a lot right now. So we'll just take a 5 minute break and come back so that we understand it better. So I'm thinking, should I stop this recording or should I just do elevator music? I think I'll do a 5 minutes elevator. Okay, so we are back. I hope I'm audible. Yes. Let's do a recap and then move to prime model. So openenv has two layers to it. It's basically defined as a modular functions for the rewards, and you have what do you call gating. Gating is important so that the RL execution can fail fast. OpenEnv is actually a fast API server deployed using Docker. The environment has two layers to it: orchestration interface and the agent interface. The agent interface is the one that the tools that the agent has access to. Orchestration interface is required for training the environment, like stop, start, reset in the environment that the agent should not have access to, but is required for training. Now let's move to prime RL. So rubrics is the reward. Reward can be multi-layered instead of giving one single reward, which is shallow, and it has gating to it. So prime RL is basically an infrastructure to train these kinds of environments. So prime RL splits the RL loop into three distinct distributed processes: inference service, often VLLMs. Okay. So inference service, often VLLM, the rollout winner workers, those holds the model weights and rapidly generate text interacting with the your open-end container to gather trajectories and rewards, trainer and orchestrator. So prime model has three parts majorly for training: inference service, trainer and orchestrator. Trainer, orchestrator. The trainer, the mathematical engine it uses. Trainer is the mathematical engine it uses. The PyTorch and FSDP2 for sharding across GPUs to calculate the loss and update the model's weight based on the rewards gathered. Orchestrator is the traffic cop. It collects rollouts from inference, batches them, sends them to the trainer, and then broadcasts the updated weights back to inference. So we have three parts: inference service, trainer that has the PyTorch or the mathematical function, and FSDP2 for sharding across multiple GPUs to calculate the loss and up the model weights based on the rewards gathered. Orchestrator is like the cop that basically update the model weights in the inference service. It collects the rollouts and inference, batches them, sends them to the trainer. It collects the rollouts and inference and batches them and sends them to the trainer. That's updated weights back. To maximize throughput, the prime RL actually runs asynchronously. The inference workers do not sit idle, waiting for the trainer to finish calculating whether they keep interacting with the critical system variable called policy staleness, controlled by max sync level. Policy staleness is how much inference services are allowed to fall behind the trainer. Controlling. What classical algorithms discussed earlier, where the model learns where the action will just happen. So if we keep the max sync level too high, the training process can collapse because max sync level basically means how much the inference service is allowed to lag behind the trainer service. So it can lead the model to go into, I'm not sure actually, it can lead the model to go into a loop that is deteriorating, but how? Why? So let's see. Distribution shift resulting in policy collapse. So if we set it too high, it can lead to policy collapse or distribution shift. This is rolled out using an old version of the model. Training is calculated against of this model current. We now have a computer. Which page is that? State, status, should not move and map this to actual. With a stateful file and execution, our first stage is to define the two. Okay, I'm coming. Okay. So basically, why we are learning all this? Because we want to attempt this.
Okay. I hope this is now clear to everyone.
So what we'll do is
All
create
right.
one. Use no. I don't want to do it in the fast mode. Whatever. I want it to be the best mode. Yeah. No. Uh, Wait. Can I change the default? film. I added it here itself. Nice. So based on this, let's try and so it's really cool that I was able to do this. Okay, let's create new documents, coding. Virtual and so what we're trying to do is now based on this video we'll try to set up the basic open-end environment and see if we can execute few things. So we'll go through the code to understand it better and just ask what all we don't understand as of now. Okay. Uh, so in the meantime, we'll go through the commands. Still add. To be valuable for training, your environment should simulate complex real-world tasks like food delivery, bug fixing, flight booking, or healthcare triage, like Wordle or Echo. A strong environment handles long-running tasks with multiple decision trajectories. Okay, let's open it with let's go through it. To be valuable for environment should complex real world tasks like food delivery, fixing, flight booking, design rich rewards again, reward pass fail score, use process support and partial rewards for steps in right direction. Pass the student achieves a reward. Uh, okay, let's see. So we have code. Let's go through the code. So this is the entire skill that we have for the code. This is the sample environment that we created. Let's go through each file line. This code for let's just focus on understanding each file. And understand each file. On the open and don't make any. Okay, so the remaining task, what I want to achieve is today is the deadline for this thing. So I started it late in hopes that because of AI, I might be able to do it. Let's see if we are able to do it well and good. If not, it's still fine. So at least I would know better than I used to know one day before. Increase deploys automated thing to Yeah, so let's go through it once and for all.
Okay, I'll get started. So, as we've heard, openenv is kind of based in two places, right? It's based in the GitHub repo. Okay, I'll get started. So, as we've heard, openenv is kind of based in two places, right? It's based in the GitHub repo, and that's where all the software. Okay, I'll get started. So, okay, I'll get started. So, as we've heard, openenv is kind of based in two places, right? It's based in the GitHub repo, and that's where all the software is, and all the tutorials and the documentation. And it's also based here on the Hugging Face Hub and the openenv organization. And this is where all of the envs are in their like running and usable state, right? So this is where the envs are distributed. This is where they're deployed. And this is also where you will distribute and deploy your M's, and that's how you'll submit, right? So if you just take a look here on the hub, you'll see there's a README here that is in fact almost exactly the same as the GitHub one, just a bit more concise. It gives you the snippets there that you'll need. Down here, you'll see these collections. These are probably the most important place to come. You'll see a set of collections for different environments. Here's just a mixture of the latest ones, Environment Hub v 2.10. That just means that these environments align with that version of the software. All the others are kind of just like categorical, like we've got some real world agents here. So a calendar environment, a reasoning environment, web search environment. You might want to pull these in packs or if you were using a multi-environment. And then we've got like reasoning games there, and they're just kind of categorized. Okay, so your objective. Okay, I'll get started. So, as we've heard, openenv is kind of based in two places, right? It's based in the GitHub repo, and that's where all the software is, and all the tutorials and the documentation. And it's also based here on the Hugging Face Hub and the openenv organization. And this is where all of the envs are in their like running and usable state, right? So this is where the envs are distributed. This is where they're deployed. And this is also where you will distribute and deploy your M's, and that's how you'll submit, right? So if you just take a look here on the hub, you'll see there's a README here that is in fact almost exactly the same as the GitHub one, just a bit more concise. It gives you the snippets there that you'll need. Down here, you'll see these collections. These are probably the most important place to come. You'll see a set of collections for different environments. Here's just a mixture of the latest ones, Environment Hub v 2.10. That just means that these environments align with that version of the software. All the others are kind of just like categorical, like we've got some real world agents here. So a calendar environment, a reasoning environment, web search environment. you might want to pull these in packs, or if you're using a multi-environment. And then we've got like reasoning games there, and they're just kind of categorized. Okay, so your objective will be to, as I said, to publish one of these hens, and that's what I'll show you first. And the other part will be to publish a blog post, and I'll also show you that. So everything I'm going to say is based on a tutorial, which is also in the GitHub repo. As we've heard before, openenv, or so meta/pytorch/openenv, and just go to this tutorial directory. And what you have here is actually a kind of repetition of other information that's spread out, but it's a bit of a like one-stop shop where you can come and kind of go end to end and walk through the process. So it's a nice tutorial to go through. You'll see that there's the first page, environments. That is really a repetition of everything that Sanyan went into. And so we won't go into that now, but it's just in a markdown format, so you can just kind of read that. Works quite nicely on mobile, but it's probably not the best way to kind of build on top of it. You might want to go to the notebook to build on top of it. Then there's a deployment page. That's what I'm going to focus on. And then we've got another page on scaling. So this is, let's say you've got this ends and you want to go to multiple GPUs or multiple.
Okay, so I guess I have to go now as I have my parents calling me. So I'll start with this session, continue with it once I'm back. It was lovely learning alongside the void of internet. Thank you.